It feels like Friday to me.
Jensen,
Yeah. What's up, Russ?
um, I just wanted to let you know I don't know if you saw it, but I sent a couple emails to you and Van Ness. I've been figuring out my OPT thing again this year.
Okay.
Um,
I'll take
there's
a
a
look.
couple. It's just a couple forms to sign, but you can do it. You can do it online, like you can do it on the laptop. Just put your initials on there,
All right, good.
and then so that's all it needs. But just so you know that it's there, because I'm trying to send it all off by this weekend.
Okay. Yeah, I'll take a look after class.
All right. Thank you. All right.
Yeah. All right, let's start. So we'll wrap up-ish the hyperbaric stuff for the diving. We could go just down, the cave, go spelunking into our favorite grotto, whatever. And you're going to get some of this response, but you're going to get a lot more pronounced response if you have that hydrostatic pressure, if you have the water applying pressure to you as well, where it's not just the partial pressure of gases, but you also have just the atmospheric, you also have that hydrostatic pressure. And so we'll spend today talking about going underwater with equipment that's a little more sophisticated than this. But just a reminder of where we've been. We have to preserve homeostasis, and homeostasis is a lot more complex than we talked about at the very beginning of the semester, where it's just like, well, blood gases. I mean, there's just so much more than temperature and the way we're sensing a lot of these things. You remember the pressure, that's going to be your baroreceptors, and let's go through the medulla for this stuff. And we'll have an inhibitory effect to calm down that pressure, have an inhibitory effect on our sympathetic nervous system to relax that pressure. And then the chemoreceptors, are going to live in the same area, right? So in that same area, we'll have chemoreceptors, which will say, all right, here's a concentration of blood gases. So we know the blood pressure from the baroreceptors. Now here's the blood gases. And there are some inert gases, right? We talked about argon and nitrogen and some of these gases that they're not metabolic, right? The oxygen, the carbon dioxide, those are our metabolic gases. But those inert gases do come in as we adjust the pressures, as we adjust the atmospheric pressure on our tissues, and sort of shove those gases into those tissues. The balance between acetylcholine and norepinephrine, that balance between the parasympathetic vagal nerve stuff that calms you down and the sympathetic nervous system speeds you up stuff. There's the vagus nerve. We're going to talk more about this today, and it's not like vagal hijacking is my coinage. That's not like a scientific thing. So if you type vagal hijacking into PubMed, that's not going to come up with some sort of response. But that's what you're doing. You are interacting with the vagus nerve in a way that makes it think there's some sort of environmental pressure, or stress, or episode of some kind that it needs to respond to. What are you actually doing? You're gagging yourself, right? Or you have the diving response. We're going to talk about that one today as we talk about diving and what happens with that mammalian diving response, the diving reaction or the diving response. You remember what the heart rate is going to do. Now, with diving, sometimes you're going to speed up the heart. Sometimes you're going to slow down the heart. It depends on the nature of the diving experience. But the cardiovascular response, what the heart is doing and what's happening in circulation with vasodilation, vasoconstriction, to accommodate the changes in blood gases, to accommodate the changes changes in pressures, you're going to have a bunch of this stuff happening. Is the water cold? Is the water warm? What's your depth? All of that stuff is going to matter. Adenylyl or adenylate cyclase. Let's create some cyclic AMP. Cyclic AMP over here, right? This would be regular AMP over here. You do have enzymes to convert that into that. It's called phosphodiesterase. But you're going to take your ATP, convert it into cyclic AMP, and then with a cyclic AMP, that's your second messenger to prevent calcium in. Let's get that heart going, right? Let's have the action of sympathetic stimulation. Norepinephrine is a neurotransmitter, but the neurotransmitter doesn't directly activate anything. It has to bind to a cell surface receptor, an adrenergic receptor, and then initiate some sort of signaling cascade. And for this one, let's build up a bunch of cyclic AMP and get some calcium movement in the heart, as opposed to the vagus nerve, which is doing the opposite. Let's decrease the concentration of cyclic AMP. You know what your order of blood vessels are, and how that stuff works. And this is a lot of the accommodation that you're going to be seeing with the diving response, and kind of plunging down into depths, is vasodilation, vasoconstriction. That's what the blood vessels are going to do. That's the only way they can really control where the blood is going. And the heart, right, you have stroke volume, like how much blood is in every beat, and then you have heart rate, how fast is that thing going, and all of that stuff is going to be adjusted as you go down. Pressures get changed. We sense pressure all over the place, really, but the aorta and the carotid are the high pressure zones for both chemoreceptors and the baroreceptors. But we do have low pressure sensors to see how much total blood volume we have. Now, if you're changing the overall pressures in your body, you're going to start noticing some of these things. It may not be a cardiovascularly imposed pressure difference. It could be an environmentally imposed pressure difference, and you're going to notice, right? You're the baroreceptors, or if you have, blood gases that are being affected by the pressures. It's not like your chemoreceptors and your baroreceptors like, oh, that's right, he told me he was going to go scuba diving. I got this. Don't worry. I'll put in a little correction factor. They just respond. They just respond as though it's a normal thing, and that is what elicits some of the problems that we do encounter if we ascend too quickly from the depths, stuff like that. You know how ventilation works. You move a bunch of air in and out of your lungs. Here's what's in the air, right? There's some inert stuff that becomes important when you're doing, scuba diving, when you have an artificial source of air, of something you're breathing, this compressed air. It's not like just pure oxygen that you're breathing. That would be toxic. And so we have there's a bunch of nitrogen in there. I mean, it's compressed air. And but those inert gases do become potentially problematic on a fast ascent. But these are the two metabolic gases, right? We consume oxygen, we produce carbon dioxide. And, ventilation and respiration, the difference between those things. Respiration is the physiological and biochemical stuff of the exchange in those metabolic gases. Let's, use up that oxygen and produce and exhale, excrete that carbon dioxide, all about surface area. And so as you get into the alveoli, the surface area there surrounded by capillaries, that's how all that gas exchange is going to happen. But remember that surface area can be affected by pressures. The pressures in your lungs, let's say there's a ton of pressure. Like if somebody's giving you a huge bear hug, you can't do like deep yoga breathing. like all that stuff where you make noise. And whenever I go to a yoga class, they're like, all right, now I want you to exhale, but make the noise. Be as relaxed as possible and make the noise. That's the only part of yoga that, so Genevieve, if you do that, I would be uncomfortable during that moment. Like, all right, I want you to just relax as you breathe out and let that noise come. Like everyone in the room does. Like that to me is not relaxing. That's deliberate. Otherwise, when I'm asleep, I would be doing that anyway. If somebody is bear hugging you, you can't do that sort of yoga breathing because there's too much pressure. And so you can't open up the lungs as much. You don't get as much lung compliance. And so what you need for exchange of gases is surface area. And you don't always get it when you're at depth. Just the order of things. You have to get into little tiny, tiny, tiny stuff where the gas exchange happens. Little tiny, tiny, tiny blood vessels, little tiny, tiny, tiny alveoli, maximum surface area. And now we'll get to this more and more, as we talk about altitude. Today we're going in depth though, but the higher altitude you get, well, first, the higher your VO2 max, the better you're going to perform. But the higher that you get in your altitude, the worse your VO2 max is. And VO2 max is this critical determinant of how much oxygen can you actually use. You breathe in a bunch, and then you breathe out less than you breathed in. And the amount, that difference, the difference between how much you breathed in and how much you exhaled is the foundation of aerobic metabolism. You're going to perform really well if it's a huge difference. You're going to perform terribly if it's a tiny difference. And when you get up into altitude, you're going to perform worse and worse and worse and worse because you don't get to use as much oxygen. You go into sea level or depth and you get to use more oxygen. You get extreme about it and it gets dangerous though. And so there's a healthy optimal performance altitude that you can perform in. But if you go too much lower than that, you're looking at some potential problems with pressures. Blood. We have a bunch of red blood cells, tons of red blood cells. That's your hematocrit. We're just constantly making just millions of these things every second. Before I finish this sentence, the collective, the fellowship of our class has made like 1 billion. I mean, we make so many of these things all the time, and that's our hematocrit. And this is another domain of regulation, of homeostasis. If that hematocrit gets too low, good luck carrying enough oxygen to support your basal metabolism. If that hematocrit gets too high, good luck pumping that blood around. Good luck pumping that viscous, like, gelatin around. Hemoglobin, right? That's the primary protein in your red blood cells. If you're a adult, if you're like born and you're living and you can hear this sentence and stuff, then you have a couple of alphas and a couple of betas. Babies have a couple of gammas too because they have to sort of leach, they have to siphon some of that oxygen off of mama. But this is roughly 99% of the oxygen we're delivering through the blood is going to be on board hemoglobin. That's the primary transporter. That's a primary mode of oxygen delivery is going to be hemoglobin. And whatever, you have a lot of it, and you're maintaining this to some effective degree. If you're a really good aerobic athlete, your hematocrit's going to be a little bit higher. If you have terrible COPD, your hematocrit is going to be even higher, but that's sort of a problem. Now your oxygen competes with a bunch of stuff, and they're allosteric binding. So remember, allosteric is not the active site. Allosteric, if you're an enzyme, that's not the site where you're going to perform the chemical reaction. If you're some sort of receptor, that's not where the actual ligand or whatever, hormone or cytokine or whatever it is binding. For hemoglobin, an allosteric site. That's not one of those 4 oxygen sites. It's binding somewhere else. And so that's carbon dioxide. As you accumulate carbon dioxide, you do a bunch of aerobic metabolism and carbon dioxide is generated. Part of that carbon dioxide is dissolved in the blood, but part of that carbon dioxide is allosterically bound to your hemoglobin. And so that's how you are delivering some of the carbon dioxide to your lungs to breathe it out. Other stuff is competitive inhibitors. Carbon monoxide, which is why we have these detectors, is like 250 times the affinity for hemoglobin. So if there's a little bit of carbon monoxide in the air you're breathing, that's what you're binding to your hemoglobin and transporting instead of oxygen. But you're not metabolizing carbon monoxide. That's not what you need in the electron transport chain. How many red blood cells you have, right? This is controlled by the kidney. That's EPO. That's the aerobic drug. My hunch is that 90% of NBA players are on both steroids and EPO, and 100% are on at least one. They don't do drug testing after, I think, rookie year has like random drug testing. After that, they don't. And you look at the performances of people in the NBA, and like that's not what a human does. And you say the same thing about cycling. You say the same thing about most of these sports. That's not actually what a human body does. You need drugs to be able to have that sort of blood volume and oxygen carrying capacity and capacity to get physical recovery capacity to get back on the court the next day and to not look like, your legs are like broomsticks and stuff with all of the AMPK activity, and like LeBron James's shoulders are still like Arnold Schwarzenegger's. So we control this in the kidney, or you control it by like exogenous, right? You can just like take stuff to create more red blood cells. Now, Henry's law, this is going to come in more today. Henry's law and Dalton's law and Boyle's law, these laws that we've been talking about are going to come in at the end today when we're talking about what happens when you're under the water. But remember the soda can, right? You open up, you pop the pop can top, and that does that thing. It's releasing pressure. That pressurized air that's above the fluid, that's Henry's law. That is carbon dioxide. It's concentrated. There's a higher concentration of carbon dioxide in that air that's above the fluid. And so it makes the carbon dioxide stay dissolved within that water. If you change the partial pressure of that carbon dioxide, if you change the partial pressure, it permits carbon dioxide to escape the fluid. And so that happens as soon as you pop the top. I guess if you like pop the top and go and like sniff it, maybe you'll get like a little extra carbon dioxide. All it's going to do is drive your breathing. I mean, it's not going to be enough to change anything, but you get what I'm saying of what Henry's law is. Yeah, there's some of the oxygen that's delivered to your tissues, to your metabolically active tissues, is dissolved in your blood. It's not sitting in one of those taxi seats in the hemoglobin. It's actually dissolved in your blood. And the higher the partial pressure of that gas, the more you're dissolving in your blood. And so that's what leads us to, the NFL sidelines. And I don't think that's the optimal. I don't think that does anything, because oxygen is not really a piece of that recovery necessarily. It's not critical to like, okay, you exercise for 3.5 seconds. What are you talking about? You need to sit there for like 30 seconds on oxygen. That's not really how metabolism works. But during actual performance, there does seem to be enough evidence to say that supplemental oxygen is going to enhance performance. Now, it's not across the board, everyone ever, in whatever you're performing, in every athlete, in every context, at every age, and that's not what I'm saying. But going back to Roger Bannister, the guy who broke the 4-minute mile, his original publication right around the time he wrote it, right before he broke the 4-minute mile, talking about, when you inspire, when you take in, when you breathe in a bunch of concentrated oxygen, it changes your breathing. It depresses ventilation. Yeah, because chemoreceptors. We have chemoreceptors like, whoa, there's a ton of oxygen here. Let's back off on all this breathing. And so you're going to try to regulate things, right? Blood gases. That's one of the things that homeostasis has its eye on. That's one of the things that homeostasis decides, like, okay, this is something we need to regulate a little bit, because too much or too little, both is a problem. Either of those can be a problem. So we're going to have to regulate that. And carbon dioxide, let's notice these things. Let's send messages to the medulla to regulate breathing accordingly. But during performance, when you're actually using all of that oxygen, right, you are consuming it at an elevated rate, and you can see arterial oxygen saturation falling during intense exercise. Not like while you're walking, it's like even higher than when you're sitting there. But while you're in more intense exercise, you're running and breathing really in a labored way, and you're 75% of your VO2 max and whatever, you're exercising hard. Your arterial oxygen saturation is going to be strained in those situations, in those sorts of exercise contexts. And having supplemental oxygen, you do see improved performance, right? So what you're seeing in this one is improved pulse oximetry. It just means the oxygen saturation, arterial oxygen saturation. Oxygenation of the tissues. There's the brain, there's the skeletal muscle, it's higher, right? But the heart rate is lower, right? Ventilation is lower. Remember, we have those chemoreceptors that are trying to regulate blood gases, and we don't need to overbreathe if we have an excess of oxygen already. I mean, look at the arterial oxygen saturation. Why do we need to breathe so much? Well, because we're working out really hard. And normally when we work out hard, we breathe really hard. Yeah, but my oxygen in my blood is like awesome. There's no real. I'm gonna hold my breath for. I mean, so that's what the chemoreceptors are informing your medulla, and you're changing this stuff, right? You're changing what would be doing this is now doing something closer to this, right? You're doing something closer to like not really total lung capacity, but a larger inspiration, a larger exhaling, and more rapid breathing. The ventilation is going to try to match perfusion needs. Boyle's law, just think about diving. Think about, as you get deeper and deeper and deeper, let's say you're in the water, the pressure gets higher and higher and higher. If you go up the mountain, the pressure gets lower and lower and lower. But as you get deeper and deeper and deeper, the pressure is going to get higher and higher and higher. And it's going to start to look like that. Not that, but that. Not that, but that. You get the idea. The volume and the pressure of these gases are inversely proportional at a consistent temperature. And those gases, the behavior of those gases, our metabolism and the fate of those gases is in part determined, in large and very large part determined on pressures. And these pressure gradients, that really gives them the direction, that tells them where to go. We're not really going to talk about these laws as much. There's more. Dalton's law. We are going to talk about this one today. Remember the total summation of gases, that's the total pressure. That is the total pressure. But individual pressures determine where those individual gases go. Henry's law cares about this one over here. Henry's law would care about this one. Dalton's law says, all right, we're summing these things up. There's a total pressure. But the partial pressures determine where these gases are going. So in the atmosphere, right, this is like normal numbers for the atmosphere. The partial pressure of oxygen is pretty high, 160 or so. You get down to the tissue, the metabolically active tissue, the partial pressure of oxygen is very low, under 40 or so. And so just gases move according to concentration or pressure gradients. And so, if you're looking at ions, that's more concentration, electrochemical gradients, and these pressure gradients, that's going to be the gases. And remember the way that hemoglobin works. We have an oxygen dissociation curve, and stuff affects it. If you're over here, pH of 7, that's more acidic, meaning, here's, pH of 7.4. This is more basic. This is more acidic down here. uh, we're releasing the oxygens from the hemoglobin with more ease. Same thing with temperature. As temperature goes up, same thing as carbon dioxide accumulates, same thing. We're releasing it with more ease. And then that 2,3, the DPG or BPG, that bisphosphoglycerate or diphosphoglycerate, that is another thing that's just helping the hemoglobin release its oxygen. But we have to have the curve be preserved for quite a while, and then we see this steep drop off. I mean, just we're at the precipice over here, and then you just go tumbling down, into the ravine floor or whatever, and into the fire swamp. And but it has to be that way because nature gives us so many interruptions. As I'm talking, I'm not breathing, and that's going to change the partial pressure of oxygen. If you have a period without breath, these gas pressures are going to change, and we have to continue to saturate our blood at risk of devastating consequences. You choke on a Skittle or something, or you go underwater for a minute or so. You have to be able to preserve the oxygen. And as soon as one oxygen binds, it actually changes the shape a little bit, and it permits the binding of more. But you do see this steep curve that way, so it takes a while. Okay, let's get into some diving. There's it's like at the bottom of a fishbowl or something like that, the little treasure trove. You're gonna dive down into that thing or spelunk into it or something like that. If we're going to be doing some scuba diving, right, we have a tank right here with compressed gas, and we would be breathing both metabolic and inert gases in that tank. It's not just pure oxygen that you're breathing. They've done some of those experiments. There are hyperbaric and hypobaric chambers that you can rent or use, or sign up for, or whatever. At some point, maybe we'll get one at Pacific. I would happily spend a lab budget on a chamber, and then we could do experiments to see what does it feel like in a hypobaric chamber, a low pressure chamber, simulate altitude. Right. Okay. Now you're at 10,000 feet. Now you're at 12,000 feet. What does a hyperbaric chamber feel like? What is your oxygen saturation as we descend farther and farther below sea level? So you can simulate these things in a laboratory setting, or you can put on some, dolphin attire and do it in the real world, sort of. We're not that good at, aquatic stuff. Or, there are places in the world that descend pretty low. Just dig a huge hole in your yard and go down a long way. So hyperbaria, this is gas pressure is high. Environmental pressures, right? So there's a standard atmosphere. This is the unit of measurement. This is what it's measured in. There's lots of different, what one atmosphere equates to. Man, there's a lot of stuff, but 14.7 pounds per square inch, fine. Okay, it doesn't matter. Nobody's going to ever ask, and that will never come up. But that's what one standard atmosphere means. Think of it from the perspective of MET values, a metabolic equivalent of the task, a MET value. That's a MET value of 1 means you're resting metabolism. well, what the hell is your resting metabolism? Like well, the amount of oxygen you're consuming in a minute and whatever. Like, okay, we can measure resting metabolism in a number of like, what's your ATP consumption or whatever. I mean, metabolism is a complicated uh, set of environmental of chemical reactions. This summation of all these chemical reactions. We have one met. That's your metabolism at rest. Okay, that's one standard atmosphere, right? So what's two mets? Well, two mets is double your resting metabolism. You're not resting anymore. You're at a twofold increase, 100% increase in your metabolic rate. So that's like two standard atmospheres, and so that's, if you think of it from that perspective, who cares about units of measurement? It doesn't matter. The way to measure atmospheric pressure, if you have one of these mercury barometers, you have the atmospheric pressure being applied here, and there's where the mercury rises. And so there are ways of measuring this, of measuring the barrier. Dalton's law, you remember Dalton's law, where we have oxygen plus, over here we have nitrogen, and then now we have the total gas pressure over here. Hyperoxia, as opposed to hyperbaria, we're concerned with the partial pressures. We're not, hyperbaria is gas pressure, total gas pressure, right? It's high. There's a lot of pressure here. All these gases, all this, the total summation here. Hyperoxia, this is the partial pressure of oxygen. Who gives a shit about number two over here? This is hyperoxia, and it's going to determine, remember, the partial pressures of individual gases. That's what's going to determine where those gases go, their fates, their destinations, where they will eventually arrive, what tissue, how much gets absorbed, how much doesn't. Is it in the blood, is it in the tissue, whatever. Partial pressures of gases are going to do that determining. Okay, so a little history of diving. Free diving is the historic, like, let's get into BC times. I keep referencing Homer, right? Iliad and Odyssey, and sponges existed in both Iliad and the Odyssey. I mean, having good hygiene back then was set you apart from the rest of society. The amphimedon, this is a type of sponge, but it's also a character in the Odyssey. Some, like, I think it was like a womanizing suitor of Penelope or whatever. But sponges, I mean, we just buy synthetic sponges. You go to the grocery store, this isn't like a sea sponge over there. I mean, that's we just buy synthetic things. You can buy sea sponges still. I mean, I don't think you can go get one from Safeway. Maybe Grocery Outlet has, a sea sponge now and again, something like that. But yeah, we used to have to just dive. Your ancestors, they had to dive, to get stuff, whether it was spear fishing or sponges, because they had to maintain a hygienic household, or competitions, even breath holding competitions and diving competitions. And if there's a shipwreck, let's go down and salvage whatever materials, sort of little precious gems or something, or maybe there's pearls down there, there's some sort, whatever it is. We have a long history of finding ourselves at depths, and for a extraordinarily long time, there was this idea, like the 4-minute mile. We've been talking about Roger Bannister, the 4-minute mile. This idea of about 100 feet or so. There's like, oh yeah, how do you get beneath 100 feet? I mean, that's really far down. We had these different depths. There's the 2-hour marathon. We have all these sort of achievements. But if you're free diving in the days of yesteryear, right, rewind the world some centuries, and depths were this, I don't know, it's like outer space or something. Like, how high can you jump? The moon, right? That's not something people would have, that was a bigger deal breaker than the 4-minute mile, right? I went to the moon. but we have a long history of diving, and today we have Guinness Book of World Records um, goals that people really just go for it. And for a while, this was the lady, right? So she was just any diver, male, female, whatever. So this is 2002, 160 meters down. Now that's not like just plug your nose and kick. No utensils, right? I want you to just use your God-given biology to worm your way down there, right? And people have these like high-tech gadgets I mean, look when they do these uh, what would be free dives. I mean, they're in like these missiles. Look up this guy, Herbert Nitch. He currently has the record, 214 meters set in 2007. In 2012, he attempted to break 800 feet. He got there, but it's not, the record doesn't count because he ended up with narcosis, right? And we'll talk about narcosis at the very end. So I don't think that record counted. It didn't that didn't end well for him. He's alive. Took a really long time to recover, and right away I mean, I think on social media, oh, I'm alive or whatever. And he recovered for a long time in silence, and then I don't think he's attempted it again, but he has ambitions. Last I heard, he has ambitions. But this stuff gets tough. I mean, go down with that pressure and like open your mouth. But watch when he goes down, open your mouth, and it just comes like flooding in. And like if your eyes are closed, you can see stuff sort of. There's like I don't know, like a night sky or something. Everyone close your eyes and look into your eyelids and like aim yourself at the light, and you see stuff. You see like little, like, I don't know, collagen swimming around there, like little worms or little tapeworms or something. You have vision. Open your eyes and the world just floods in. It would be similar to get 800 feet down, open your mouth and the world floods in. I mean, this is a high pressure space. And uh, but if you look at the videos, I mean, he goes down in the equivalent of like, a NASA rocket ship. He goes down and he like goes up with balloons and stuff. I mean, it's all technology that's going to deliver him to the bottom and to the top, and that technology doesn't stop him from having like nitrogen narcosis. So some stuff can go wrong, right? You get in that missile, you get in like the NASA built, it's like something between the Challenger or like Apollo or something and a soapbox derby car. It's like something between that they go down in. And you go to this deep depth, deep for us. It's not like the Mariana Trench or something. And lots of physiological changes are going to manifest. Okay, we'll go through these ones to some degree of we're not going to go to 800 feet depth on any of these, but breathing. Yeah, you have like artificial stuff usually when you're down there. We're not talking anymore about free dives. We're just talking about being a human being. You're a scuba diver. You throw a tank on your back and you hang out downstairs, right in the basement of whatever ocean or something that you're in. This isn't like you're a world-class, free diver or whatever. You're going to be breathing down there, and breathing is going to get a little bit affected, even if you're just floating there, your head, or you're like snorkeling or something, your head is out of the water. You still have increased pressure applied to you. The work, the labor of inspiration. Now the expiration, the exhalation, the breathing out, that's fine, whatever. That's a passive activity, made easier by the application of external pressure. But the inhalation, breathing in, that's a little bit harder. And lung compliance, right? The ability to that elasticity and the ability to create this gas exchanging larger surface area, that gets compromised a little bit. Vital capacity. Remember the breathing uh, that breathing image of that old guy and the little line coming out of his mouth, and that gets much harder. You can't do that as effectively. It's more and more work. And then those pressures are going to cause the absorption, especially you go down into depth. You're not just like floating there anymore, right? You're going down into depth. You have a little breathing tank on. That compressed air that you're breathing is not just pure oxygen. There's a bunch of stuff in there. Inert gases will be absorbed more owing to that pressure. That matters later. But immediately the absorption of those metabolic gases, right? Oxygen especially, um, is going to be higher. You're going to absorb more of that oxygen. But then that mechanical work of breathing, right? More carbon dioxide, more metabolism happening from the mechanical work of breathing. But you get too much oxygen, reactive oxygen species, you're going to generate more of those. Those are free radicals with oxygen in it. Superoxide is the one we all talk about, right? At the end of the electron transport chain, you prematurely leak electrons. And so you get this unpaired electron. And you remember from like for 129 or whatever kind of elementary physiology classes, the electron transport chain. Um, uh, the cytochrome C oxidase at the very end, that's the thing the cyanide's inhibiting. If you prematurely leak an electron there, which happens, that's going to happen with elevated metabolic demand. I mean, you're really running. You're doing the mile or something. Running a few miles, whatever. You got your 10K, let's say, and you're going at it in that 10K. You're going to create a lot more reactive oxygen species, just like the male. Or just like, there's times of the semester where, like, I'm sure everyone's pissed at me. I mean, like, especially the people who need response, like Ross, you knew what to do. You just like, you send me a text and or you at the start of class. But man, when I get a lot of emails and stuff, it's hard for me to get back to them. And so I make more, let's say, social mistakes or whatever, or like lack of correspondence grievances, however you want to call it. UPS and USPS and FedEx, if it's December 20th, they're going to fuck up a lot. And it's the same thing with your metabolism. If your metabolism is really elevated, you're going to create a bunch of free radicals. Now, all you need to do is breathe like high concentration, high partial pressure of oxygen, and you're going to create a ton of reactive oxygen species. And this can poison you, right? This becomes potentially very damaging, very detrimental. Acutely, yeah, okay, maybe there's a risk of a seizure or something like that, but the oxygen toxicity with prolonged hyperoxia, you can cause lung damage. I mean, this can get terrible. And so too much oxygen, this gets a little bit bad. Now, the diving response, remember that mammalian diving response or that diving reaction? We talked about this when we were saying, everything but that like digital rectal massage seems to work through the the vagus nerve. And there are different routes to get to that vagus nerve. There are different cranial nerve on ramps to get to that vagus nerve. And then the vagus nerve releases acetylcholine. But there are afferents, there are efferents, right? The efferent, the motor part of the vagus nerve, is going to release the acetylcholine. But the diving response, right? You're a person who doesn't breathe underwater. We're not mermaids. You don't breathe underwater. And so if you submerge yourself underwater, now you can do this just in like your bathtub or kitchen sink or whatever, like a kiddie pool in the backyard, whatever it is. Just dunk your face. It has to be a little bit cold. That's really going to set in this effect for about 10 seconds, right? The trigeminal nerve, number 5, O-O-O to touch, T, trigeminal. The cold stimulus, you're going to notice that. Apnea, the lack of breathing, in combination with that cold sensory information, gets relayed to the brain, the afferents. The vagus nerve releases its acetylcholine. So what happens now? Acetylcholine, right? We slow the heart rate. We get bradycardia. We get the slower heart rate. Now, it gets a little bit weird when we have competing inputs. This one, hypothetically, is to try to maintain our tissues, right? Okay, we're underwater, we're not breathing. Let's slow things down a little bit. Let's get a little bit vagal here. That way, we don't need some racing metabolism and we don't have the ability to restock our oxygen supply. But so that is the mammalian diving response. One thing that you'll also see is, it is generally held that the diving response causes blood and lung oxygen stores to preferentially be distributed to the heart and the brain. And so that's another indicator, again, generally held. This isn't, these aren't like hard laws. If I say something about size principle or some phosphorylation thing or whatever, sometimes there's stuff that's just accepted, that, oh, this is how it works. And is it likely to be overturned? Very unlikely that will ever be overturned. It's been exhibited 1,000 times and there's never been an exception. When you get into some of these why questions, looking for a purpose, stuff like that, those get a little bit hard to answer, and one has to declare them with a sense of doubt or proportion or whatever. But what it seems to be doing, this diving response, is okay. Let's preferentially send some blood to the critical areas, right? The heart and the brain. That's like number 2 and number 1. The brain would be number 1, and and then let's get a little vagal response going. You will get this response when you do like deep sea diving or whatever. Just go swimming. Go swimming in Lake Tahoe and like go under and whatever. You're going to get this response, the diving response, this vagal response. Now, the stuff gets weirdly complicated. I have not followed this chart through. It's like if you're eating you're like a 10-year-old and you get the like Fruit Loops or like Count Chocula or whatever, and you're sitting there and you turn the cereal box to the back and you do the little mazes and whatever. When I was a child, I used to just like, oh, let me follow every single route in this maze to every dead end and just understand this maze like I'm a mouse and there's cheese somewhere. What a staggering waste of time that was. But it's like I don't even do that now as like an adult looking at this thing. But it would make sense to you if you were to look at a bunch of this stuff, like um, adrenergic innervation and the hematocrit with the heart rate and the cardiac output, breath. What everything is on here. I mean, there's nothing here that is some weird foreign word or anything. So you could follow the Count Chocula map around, but the only point, the reason that I've included it is that it's just complicated. There's so many inputs, and homeostatically, we're trying to maintain survival. Remember nature's first great law, that the Andrew Marvell thing, Samuel Butler, if you look it up on Google, but not really him. But this idea of self-preservation, that we're trying our best. Our body is unconsciously, we're not in control of any of this stuff. How many red blood cells did you deliberately make in the last second? Did you make any of them on purpose? I got to put my mind to it. I got to make some more red blood cells. Like all these processes happen without your input. There's some conscious processing that you can contribute, right? I mean, people can slow their heart rate by, if you're a biathlete, right? You're like a alpine, legend with a rifle or something. Ski, target practice, and then you got to wait. You consciously they're able to slow their heart rates down, right? They find some zen space and, all right, I got to shoot between beats. That target's pretty far away. If I pull the trigger as my heart's beating, I'm gonna like miss the target by 10 feet and like hit a spectator or something. They are able to slow their heart rates down, and you can think of a panicky thing and speed it up. Just think of some imagine, and maybe this is true, imagine like you're concealing a crime. 8 years ago, you did like a, octa homicide or something, like hexa homicide. And nobody ever found out. You're like a serial killer. Nobody knows. All you have to do is think like, oh, I'm going to get caught or whatever. And like your heart rate goes up. We're able to consciously have some input here, but nearly everything, I mean, like 99% is a hilarious underestimation. Nearly everything your body will ever do happens without your conscious thought or even awareness. And so a lot of this stuff is a body taking these really circuitous routes to say, all right, let me interpret every possible input and try to homeostatically maintain survival, because self-preservation is nature's first great law. Okay, fluid balance, circulatory changes, fluid balance. What do people do when they have swelling? Right? Oh, my ankle is swollen. Okay, they put on like pressure. They put on like an ace bandage or whatever. Or even if you are, let's say, you sprain your ankle and somebody comes and like cuts off your shoe. Your ankle isn't actually swollen while the shoe's on it. Maybe it depends on you. Let's say it's like a high top. It's like a tight, you're wearing like 1989 NBA high tops or something, and your ankle isn't really swollen. Take the shoe off, and then now it starts to swell. So when you have pressure applied, where does this fluid go? It changes where the fluid is going. And so you start to see peripheral blood getting redistributed into that central circulation. So out in your limbs and the periphery, that blood is getting back into the core, really. It's almost comparable to if it's just plain cold and you're vasoconstricting in the exterior and circulating, blood in the core as opposed to the quote shell, so you can preserve heat. It's something similar, but this is pressure. This is pressure induced, and your venous pressure is going to increase. Remember what the skeletal muscle pump is? Not hyperemia, not reactive or functional hyperemia, which is bro science pump where you go do a bunch of bicep curls and your biceps are huge. Not that skeletal muscle pump, but the skeletal muscle pump that says venous blood pressure is super low. It's not getting back to the heart. Right, preload is compromised. We're not getting blood flow back to the heart. So what you do is you flex your muscles. Right, don't stand there on the choir bleachers with locked knees. Don't stand there in the military line with locked knees. Don't stand there in the wedding, like bridesmaid, whatever line with locked knees and like giddy with flowers in your dress and whatever. Don't do that. Like flex some stuff, flex your calves a little bit, get some little hammy and knees, vibrate in your legs a little bit. You'll look weird to everyone standing out there, but you're not going to be the one who passes out, especially in like the heat or something. If you're standing in a line and it's super hot out and you're in like San Antonio or something and you're in a wedding and there's no AC and that's the skeletal muscle pump. Is the muscle squeezes against a vein, and veins have such low pressure that it's insufficient to drive the blood back to the heart. So they need a little help, right? You need to give them a massage and say, you can do it. You got this. I'm right here with you. I'm on your team. Just a helping hand, a helping flex. And that pressure on the vein, they have those valves to prevent backflow. And so pressure on the vein just shoots that blood in one direction. It's like the toothpaste tube. You squeeze it anywhere, squeeze that toothpaste tube anywhere, and it comes out the one hole. You don't squeeze it and like it shoots out the back or something. And that's why every toothpaste tube has, at least of mine, have this fist-shaped indentation in the middle, because it works. It's fine. It goes in one direction anyway. And it's the same thing with your veins. Now, when you're in a high pressure situation, right, the water is applying all this pressure to you. What you're going to experience is it's like wearing compression pants. Right, if you're wearing the compression stockings, you don't need to flex your muscles so much. You're adding all of that venous pressure anyway. You're increasing your venous pressure. So that venous pressure is increasing. Peripheral blood is being redistributed indoors, right, to the sort of the heart of the home, and bradycardia. Now, you may already have a little bradycardia from that mammalian diving response. You may have, may or may not, it depends on the environment, it depends on the context. But it's possible that you're going to have some vagal nerve bradycardia already. But if you're increasing venous return, you're increasing how much blood is returning to the heart, you're going to decrease your heart rate, right? You're going to increase your stroke volume a bunch. So bradycardia. So your heart rate is going to slow, and every single beat is going to beat out more blood because you're just shoving so much more blood into the heart before those beats that every beat has so much blood in it. It's like, why do we need to beat as many times in a minute? That seems unnecessary. We can slow this down a little bit. And of course, this whole time, this is, I don't know, confounded by, this is, modulated by, whatever you want to say. The baroreceptors that are sensing these pressures, the baroreceptors are sensing these pressures. And with these huge heartbeats, your heart is going to notice, right? You have atrial natriuretic peptide. That's going to notice. All right, let's send some of this shit into, not literally shit, because we're sending it to the bladder. That'd be unpleasant. Let's send some of this excess to the bladder, right? We can dispose of some of this high pressure, high volume we sense in the atria. And so we're sensing all this stuff in the chemoreceptors and the baroreceptors. Fluids change throughout the body owing to these pressures, these different profiles of pressures. Now, we also have the cold shock response. Like cannonball into ice water, and what's going to happen? The first thing, as soon as you hit, they go, you gasp. Like, now maybe if you're underwater and you gasp, that's not going to end well. But that cold shock response, really the first thing that's going to happen is this little gasp, and then you're going to get vasoconstriction, certainly peripheral vasoconstriction, because it's really cold out there. And a long time ago, I mentioned that when we were talking about heat, that there used to be this argument that ice baths were not the ideal mode of temperature regulation for somebody, having a heat stroke or on the verge or showing risk, or just plain hot and needs a cool down sesh. There was this argument that ice baths, because of the peripheral vasoconstriction, were not ideal. And that's insane nonsense, because most people, you just go into ice water for a while and you're going to die of hypothermia if you don't remedy this in a hurry. I mean, it's so rapid, the change in heat. But you do get, they weren't inaccurate in their criticism that you do get peripheral vasoconstriction. And so you might get a tachycardia response, that inhalation, that inspiratory gas. Okay, I'm going to sneeze. That's going to be in the mic. I feel a sneeze coming. I hope that didn't just like damage everybody's ears. We'll talk about ears in just a second, and like airplanes and diving and why they pop and stuff. But I hope I didn't just like damage your eardrum now, before we learn about it. So that's the cold shock response. And this is one of the things that the adaptation, you actually do see an adaptation to. This is just one article, but there is a pretty rapid response, called accommodation if you want, whatever. But there does seem to be an acute and chronic-ish adaptation to the cold shock response. To this reaction that you have when you get into the water, into the cold water. Okay, barotrauma, right? So now we're looking at the atmospheric pressure. So you remember Henry's law of we have this sort of like pillar of air on top of us, just sort of weighing us down. And talking about Henry's law as the amount of partial pressures of those gases being dissolved in, but that's when we're looking at the atmospheric pressure. The hydrostatic pressure, that's the water pressure that's on you. And the ambient pressure as you're diving, this is a summation. This is both of these are applied. And these are your atmospheres. And again, who cares? Think of them as met values. They're just, here's one atmosphere, right? Now you start to dive. Okay, you start to dive. You go down to 2 atmospheres. Where does that happen? About 10 meters. 2 atmospheres is like 10 meters down. That's not that far, 33 feet or so. And you've doubled the pressure. And so the barotrauma, the pressure trauma you're going to experience. Like this is gas volume over here. So the size of a liter, you go down to 33 feet, right? Oh, it's getting kind of small. You're at half a liter. We're at 2 atmospheres. So we've cut that in half already. And you get down to 100 feet and we're at about a quarter of a liter. And then, 233 feet down here is an eighth of a liter. Uh, these gas volumes, you remember Boyle, the pressure and the volume, and this stuff matters, right? This can cause harm. This can inflict injury in us, the higher the pressure. Now let's talk about planes. Your ears pop, or sometimes just when you're driving. So I'll get my ears popping when I'm driving back and forth between California and Oregon. You're in the pass, and sometimes my ears, like you do that thing where you fake yawn, you like make a little noise and everything. The reason what actually happens is in the middle ear, right over here, your eardrum, right? You have your eardrum, and then there's the space behind that eardrum is connected to your mouth, right? The back of your mouth, and you're constantly trying to equalize pressures. But if you have this massive change in pressure, you can create either a vacuum or just too much pressure on it, and you can close off that space. So, you wouldn't like you can like do like that thing with your ears or whatever, like where you can make it click, or sometimes you're just chewing with your mouth and you hear a clicking in your ears. I assume everybody can do this. I always wondered if other people could hear it when I was a little kid, where I can just sit here and make my ears click. I don't even have the comment box open if anybody's been writing comments. There are no comments. Okay. I don't know whether to be relieved or to feel insulted and lonely. But when people, you can just sit there and just like make your ears click, and I doubt anybody else can hear that. I can do that too, Nick Lessa. But so that's all you're really doing here is it's this space, right? It's this little tube down here. And the changing in pressure, you can distort the eardrum, right? And you can create this sort of disparate forces, right? You can create these pressure differences on either side, and that's when it's gonna get maybe a little bit muffly in the sounds. It can maybe hurt a little bit. They can feel this pressure. It can be uncomfortable. Extreme pressures, and that thing can rupture. Okay, hold on. I'm reading the comments. Someone gets into an ice bath and experiences the cold shock response, tachycardia. Can they then put their face in the water to elicit the diver's response and return to normal heart rate breathing? Probably a contribution. Yeah, it's a really good question. So, if you have the cold shock response, right? You get into an ice bath and you get this tachycardia, you do that thing, you also, what can you do to get your heart rate back to normal? Can you just dunk your face in the water and stop breathing and something and get that heart rate under control? That's going to contribute. Yeah, maybe like, gag yourself a little, give yourself a little carotid massage, poke your eye, dunk your head, do a bunch of stuff. And you can probably manage it. Now, there's going to be responders and non-responders. There's going to be extreme responders and mild responders, and who knows what you are and which ones you're going to respond best to, unless you just give it a shot. But if you find yourself in an ice bath, if that's where you happen to be, and your heart's going, it's an interesting experiment. You know how the body works. You know what the vagus nerve does, and you know how to how to hijack it, and just look at your Fitbit or your Omron or whatever it is for those heart rate monitors. Look at that thing, and then let me see if I can bring this down a little bit, or just take your pulse or whatever, and just see if you can bring it down. I'll do this once in a while if my heart's going, to try different things. And yeah, I'm a responder. These things, my heart rate comes down in a hurry. But really great comment. Yeah. So if you have your heart racing from that cold shock response, can you get the diverse response? Probably. I've never seen a study, but it's a great question. Now, you're a scuba diver. You're not just on an airplane or eating your cereal and clicking your ears and whatever. If you are returning to the surface and holding your breath, that's a problem. People do this. Amateurs do this. I think you're warned. If you are taking a scuba diving class, or you're getting certified, or some instructor is just telling you, make sure X, Y, and Z. You're going to die. If you're going to go parachuting or whatever, there's going to be a couple of critical things they'll say. Don't cut everything off with scissors when you're in the air or whatever. I mean, there's going to be a couple of warning statements made for liability's sake, for safety's sake, whatever. And don't hold your breath as you ascend, especially if it's like a fast ascent and you're holding your breath, because there's pressures, right? There's the ambient pressures here. And if you seal it off, if there's enough pressure to seal off your ear, and the pressure upon that space. Remember just a few slides ago, looking at you don't have to add that. You have to go down that far before the spaces start to get really tiny, before the gas volume starts to get really tiny. Now, if you seal this off and ascend and expand, maybe you're going to pop that balloon. Right, that balloon might blow up and so you can cause sort of catastrophic ear damage if you ascend too quickly, and with the breath, not just in the ears, right? With the breath, though, especially, you look at the lungs and hold your breath, create a vacuum, create a sealed off space. And what do those alveoli do? What you should be doing as you go up is, that was the sound of me breathing out, so that you don't create a airtight space that is going to expand like a balloon and have this terrible lung damage. So yeah, don't hold your breath as you're coming up. Okay, decompression sickness, or the bends. To the best of my knowledge, this is a real picture of somebody who really went up too fast. The fish who was dragged from the depth to the top. So remember Henry's law. The Coke can, the partial pressures are determining where those gases go. How much is dissolved? How much of those gases remain dissolved is what the pressure is upon them. So you dive, you're breathing, you're taking in both metabolic and inert gases, right? You have a bunch of oxygen you're breathing in, there's nitrogen you're breathing in. And those gases are going to be dissolved. You're going to put them in the tissues, not just in the blood, they'll be in the tissues too. And the decompression, as you're going up, you have to, I mean, especially close to the surface is where you see a lot of it, but you have to ease into it. If you just race up, if you don't hang out for, oh shit, there's a shark, let me go as fast as I can. If you do that, that nitrogen is going to leave the tissues at this rapid rate. These bubbles are going to form, and the tissue damage. I mean, the bubbles can be in the tissue, can be in the blood, and these lungs can maybe manage some of this, but not if you go up kind of fast, right? And you can have these tissues die if you're in the brain. If you're having this expansive gas, this rapid expansive gas from a rapid ascent because the pressures. looking at this combination between Henry and Boyle here. Henry keeping all this stuff dissolved, and Boyle keeping the volume and pressure relationship. Okay, those two laws, a rapid ascent is going to elicit pretty rapid damage and potentially death. Now, nitrogen narcosis. Remember the world record holder in 2012. He tried to do his redescent. I think it was 2012, and then 2013. I think was when he was. You can look back and see what the date was when he was finally reporting. It's like, okay, I'm okay. I'm still ambitious, but I haven't done it again yet. And he had nitrogen narcosis. And so too much nitrogen accumulates in the brain, you pass out, and is that people will get you go below 100 feet or so. You take a good depth, and you're at a much higher risk of this. You're not going to get this from going down 50 feet, something like that. But you go down over 100 feet or so, and you're at risk of this. And people do weird things. It's like being drunk. People will do weird things. Well, they'll take the mask off and do whatever. They just do these kind of drunken weird behaviors. I can breathe underwater, and so you get this confusion. There's too much nitrogen accumulating in the brain. But also, if you dive and then you get on an airplane, it's not like, well, I had a slow ascent. I made it to the surface. Now I'm 100% fine. I'm fine because I took a slow ascent. My body has 100% recovered. No, that's not how it works. There's a House episode on this, actually. I think JP will be able to report if that's what this was. I remember there being some House episode where somebody's sick on a plane, and I'm pretty sure it was the bends that he had, decompression sickness. It takes time to finish. So I would not get off the plane, get off the boat, and hop on the plane. JP says, I remember that episode vividly. Okay. So the hypoxic blackout, this might be the last one that we do. The loss of consciousness, the blackout, the loss of consciousness. And this happens, right? People do this on occasion. There are a few things that can cause it. There are a few behaviors and physiological interactions that can cause it. So one of them is just again the hypoxia at ascent. What you do, the hypoxic blackout, if you're low on oxygen, right? Your oxygen supply is very low. So Boyle's law, right? The surface pressure. Remember, these gas pressures are going to we're going to absorb and use these gases based on pressure gradients. So the air you breathe, that partial pressure of oxygen, the partial pressure of oxygen in your blood, the partial pressure of oxygen in your tissues. These gases are delivered and consumed based on these pressure gradients. So if that pressure gradient, if you start to ascend and ascend and ascend, and you lose that pressure, it's possible that you're going to lose oxygen at a rate your body was not ready for. I'm feeling fine. I'm feeling fine. I'm feeling fine. Now I have no oxygen. So that would be the ascent blackout of the change in the partial pressure of the oxygen owing to applied pressures. Hyperventilation. If you've ever done one of these, just with friends, you're at like a hotel pool or something, and who can hold their breath the longest or something. It's easy to hold your breath longer if you go and then go under, right? Because you're not really increasing that much oxygen, a little bit, sure. But what you're doing effectively is expiring more carbon dioxide. And those chemoreceptors, they're your need to breathe, that biological drive to breathe. Man, carbon dioxide is important, the concentration of carbon dioxide. So if you can expel a bunch of carbon dioxide before going down, the urgency of breath, of inhalation, is not as loud, right? It is not as alarming. You're not gonna like rip your head out of the water and go, you're not gonna do that thing as certainly as early. But potentially that's a problem, right? So if you, especially as you're returning to the surface, and maybe you're returning to the surface a little later than you thought you needed to, because you hyperventilated before you went down. So the accumulation of carbon dioxide is not as abundant or severe as the loss, as the elimination, the consumption of oxygen. And then you start your ascent, and in your ascent, the pressures are made, the volumes expand, so the pressures decrease, and then now like you just don't have the oxygen for it. This one is a weak explanation. This would be the third explanation, but carbohydrate depletion, if it's prolonged period of work, you're down there and you're depleting your carbohydrates, you're going to be altering some of your metabolism, some of your preferred energy substrates, and looking at more carbon dioxide being built up by aerobic metabolism, if you're favoring that a little bit more. This is a weak one. It's not nothing. This one isn't nothing, but it's a fraction of the importance of the other two. And so it's not just like, well, I had a pasta before I went down. They say don't go swimming 30 minutes. Right? This one does matter, but it doesn't probably matter, anywhere near what the other ones would be. That rapid ascent, looking at Boyle's law, and then the hyperventilation, looking at the chemoreceptor sensitivity of the need for breath, and maybe you don't ascend fast enough. So again, going back to this, we have nice preservation of arterial oxygen saturation for a while, but then there's a rapid descent. And down here, I mean, this is where you're looking at like hypoxic blackout, because you didn't know, owing to these laws, the hyperventilation and the pressure profiles, maybe a little bit of metabolic changes, but mostly these two, right? You hyperventilate a bunch and then go down, and the pressure profiles, those laws that owing about gas, you don't quite know you need to come up yet, and then whoop, that happens. So that is the end. That is the end of our depth. We'll do one round of review on depth. I'll keep a few things. There's dive tables. Who cares about this stuff? But if you're going to go dive, what is your depth, and the repetitive dive timetable and the surface interval. There's this isn't something that I do in life. This isn't a one of my hobbies. But if it's one of your hobbies, it would be wise to, you remember like the wet bulb globe temperature, stuff like that, where it's what sorts of activities should I be doing given the amount of heat? What kind of limitations should I have? Equivalent stuff exists for everything. There are these indices that you can employ to change your behavior for just safety's sake. Okay, so that's it for today. We'll start getting into altitude on Friday. Lexi, I'm reading your comment. Oh, good. Yeah, I'll let you know. I'll look through the list and let you know. Any questions for today?
I have a scheduling question.
Okay.
So I already signed up for clinical physiology next semester. But remember how I told you over the summer I want to take clinician and possibly do independent study? So what I wanted to do for independent study, I probably won't get in during the summer. So I might have to move that to fall. Is that okay?
Yeah, here's the thing. It's okay. I'm gonna just stop the recording and we'll keep talking.